Hello, welcome back. At this point we have enough basic understanding that I think I'm ready to talk about dose, which is a really important concept. I've sort of been using it loosely through the videos so far, but I want to step back and really define it carefully. So in this video I'm going to talk about dose and I'm going to talk about Kerma, when these two things are closely related, and you'll see how. All right, so now we're going to move on and actually get to what you really want to know, which is dose. Dose and Kerma, and they're related. First of all, let me just get this issue out of the way about units. What are the units of dose and also the units of Kerma? And they're really simple. It's just really specific energy. So energy per unit mass. And there's a special word for that. Energy, of course, is joules in SI unit, and mass is kilograms, so it's joules per kilogram. And as you probably already know, the special unit for that is the gray, or we write it as GY. And of course, a very common unit is the centigrade. All right, so let's look at this in terms of how energy is deposited, and I think we're going to look at dose and Kerma together. Okay, Kerma stands for kinetic energy released in medium. So to understand this, it might be helpful to go back and look at this image here of Compton scattering, and in particular to note this sort of tortured pathway that electrons and photons take as they Compton scatter, and the point being that they don't deposit the energy exactly where the photon is absorbed. It travels some range in tissue. That range is energy dependent. And so that has consequences for dose and Kerma. So first of all, let's look at a plot of Kerma as a function of depth in tissue. So that curve looks like this. It's a slowly decreasing with depth, and that's mostly simply because the number of photons decreases as you go down in depth. They're absorbed, they're scattered, and so on, and so you're depositing less kinetic energy released as you go down deeper. Now dose does not look like this curve. It starts low, it builds up for a reason that I'll explain in a minute. It exceeds the Kerma curve, and then it follows along with Kerma down to deeper depths. Now, why are these two curves not exactly overlapping? Well, this separation is really because of the range of the electrons. So the electrons travels some distance in material, and that means that for some electron that's released here, the dose is actually deposited on average down here at a deeper depth. And so the separation between these two curves is energy dependent. If the electrons have more range in tissue, then these curves are separated more from each other. Now we're going to consider this region here at shallow depths. This is called the build-up region. In other words, where the dose is building up. And this is important clinically because you'll see the dose is lower there in that region, and that's an effect that we call skin sparing. We'll talk about that a little bit more in a future video, but the fact that the dose is low there is important, so we need to understand the physics of that. So let's go over that. I like to look at this through this cartoon. This shows photons coming in to the surface of the patient, and then they Compton scatter and they create electrons, which then wander down through tissue. That's shown with the dotted line. Yeah, so here's the electron wandering around through tissue. It's depositing dose as it goes through there, right? So now in this layer here, this particular depth, I want to count the number of electrons. 1, 2, 3 that are crossing there. That's roughly proportional to the dose. So here I've got 3 electrons going across at that particular depth. Okay, now I'm going to look at the next layer down in tissue. And to do that, I'm just going to draw 3 more photons here. Okay, I didn't draw those before; they were there in the previous layer, but didn't have any electrons contributing. All right, and so now I'm going to count the electrons in this layer, this deeper layer. 1, 2, crossing this plane, 3, 4, 5, 6, right? So 6 here, and previously in the last layer there were 3. Now let's go to the next layer. And again, I'm going to draw more photons coming in, 3 more. Okay, right there. And now let's count the electrons going across. For the purposes here, I'm going to assume that this electron doesn't cross this plane. Just count 1, 2, 3, 4, 5, 6. Okay, so again 6. And then the previous layer was 6 and 3. So you'll see here these 2 layers both have 6 electrons. The reason is that that this electron stopped. It didn't get to this deeper layer. Okay. So actually, if I were to draw another layer down here, even deeper, I would see that you can see that this would also have 6 electrons. And so what's happened is the dose is built up to a certain value, and it's reached what we would call electronic equilibrium. That is, the number of electrons going in is the same as the number of electrons going out. And that's a very important concept for radiation therapy physics. The equilibrium, number going in equals the number going out. All right, so now coming back to this picture, we can understand then what's going on in this region, the superficial region. At a relatively shallow depth, you get a low dose, and that's because you don't have many electrons contributing there, right? The beam is coming in from air, so proximal to that point, there's air, not many electrons are made in the air. And so now it builds up as more electrons are made, and eventually reaches a point here where there's the equilibrium. That's a depth that we call depth of D max, maximum dose, and then after that depth, the attenuation kicks in and the dose starts to decrease. Now, one important thing to note is that how deep this is, the depth of D max, is going to depend on the range of the electrons. At a higher energy beam, the range of the electrons is going to be longer, and it will take longer to reach that equilibrium point. It'll be at a deeper depth. Okay, so then the final thing, since we're talking about Kerma and dose, I'd like to come back to is the concept of exposure and air and dose. And so when you have an equilibrium condition, which you now understand what that means, you can actually know that in air, the dose to air is actually equal to the collision Kerma in air. And we saw this before, and I think you understand it better now, but it's actually just equal to the exposure times the energy that it takes to make an ion pair, the average energy. And so actually in air, you know that it's the exposure, and this is in Rankins, and you would just multiply by the charge that's liberated in 1 Rankin. So it's 2.58 times 10 to the minus 4. That's coulombs per kilogram in 1 Rankin. And then you multiply by this W factor, which in dry air is 33.97 joules per coulomb. And so here you see the coulombs cancel. You're going to end up with joules per kilogram, which is a gray, right? And the Rankins cancel. And so this is just going to be equal to 0.876 times the exposure in Rankins. And then so this would be here centigrade per Rankin. Okay, so that's dose to air. And so if you have a little small air cavity in a beam and you're under equilibrium conditions, there's going to be some ionization in that air cavity, and you can figure out the dose to the air in that cavity. Basically, it's a little more complicated than that, but that's the basic idea. Then if you consider dose to some medium, so not to air, but to some tissue or other material that has a different Z and so on, the dose to the medium is actually just some kind of corrective factor times the exposure in Rankins. This is called the F factor, or the Rankin to rad factor. That factor depends very much on the Z of the material and the energy of the beam. So F is just some number, but there's some complex dependency on those variables. All right, so at this point you understand quite a bit about how you understand beam attenuation and dose in a patient. A lot of this is sort of at the theoretical level so far, but I will come back later and I'm going to show you how you can actually make a measurement, like a measurement in an ionization chamber, and you can translate that measurement into an actual dose in a patient. So that will come, but for now we at least have the theoretical underpinning. I'm going to leave you with a little bit of further reading that you can dig into this more if you want. And then in the next video, we're going to kind of take a step back, go back to some of the basics, and talk about, again, at the microscopic level, how do charged particles interact with matter. See you next time.